Hello, everyone. Welcome to discussion in week 9. Today we will talk about the FIR and IR design. Okay, so let's start with the two most intuitive diagram. They looks intuitive, but there's some confusing places. So it has some ripple in the passband, in the transition band, and then has some ripple in the, let's say, the stop band. Okay. So let's first discuss in the FIR scenario. So for FIR, we usually discuss the H omega itself rather than its square response, okay? And the central point in the passband is normalized to 1, and you fluctuate it within 1 plus delta 1 and 1 minus delta 1, okay? And then if we extend the lower limit, it will match a frequency. And this frequency is called omega p, okay? And we also want the stop band to have a larger attenuation. So the upper limit of it match to delta 2. And when you first reach delta 2, the frequency is called omega s, okay? Obviously, the unit is omega, which is rad per sample. Cool. So when we design the FIR filter, the two specifications are important. One is AS and the other is RP. So AS is basically the distance from the highest point to the starting point of your stop band, the sigma delta 2, okay? So this is a difference. And remember, AS is represented in decibel. So we would like to calculate them like 20 times log 1 plus delta 1 minus 20 log delta 2, okay? And this will give us negative 20 log delta 2 over 1 plus delta 1, okay? And similar for RP, let me change the color. So the RP is basically the ripple peak to peak distance in dB, okay? And similar 20 log 1 plus delta 1 minus 20 log 1 minus delta 1, okay? This will give us negative 20 log. You see the 1 minus delta 1 is the numerator, right? Because there's a negative sign here. Cool. So we get the equation of our AS and RP, okay? So we design using the window technique or any other. I would say that the main technique you need to master is a window technique. And then you need to satisfy these requirements. Okay, and let's talk about the IIR filter. For IIR filter, you have a similar set of these parameters, but they are actually defined differently, so you need to be careful. Why is that? Because IIR, we usually discuss its square response for the convenience. And you'll see that the IIR filter, the common used IIR filter, like the Butterworth filter, they are all represented in the square response. So it is good to keep them consistent, okay? And as usual, we still have a general waveform like this. Let me drop it bigger. Okay. But we now normalize the upper bound of the ripple as 1, okay? And the lower bound, now we name it 1 over 1 plus sigma square, okay? And is the epsilon square. The epsilon here is a small value, and you see that adding a small value square to the denominator will make the whole value smaller, right? And we want the epsilon to be small, so our ripples will be small, okay? And then the attenuation is described using 1 over a square, okay? So you see that a might be a relatively big value, and 1 over a square will be much smaller than 1. Okay, so this is the intuition behind this representation. And then let's continue. because we know the IR, it has analog nature. So usually we can consider it in S domain, which is a continuous time domain, corresponds to a continuous time domain. And our unit here is big omega. And its units is rad per second, if you remember. Okay, so you see that when the passband ripples end, it maps to a frequency called big omega p. Okay, and when it starts to attenuate at the stop end, the frequency is called big omega s. So you see that for the similar specifications, they're actually using different parameters to represent it. So you should be careful during the computation and don't mix them up. Okay, and you should also notice that there is a square here, and similar for your IR filter. I mean the common used IR filter. So let's take the Butterworth as an example. Oh, by the way, so these values are not represented in dB. So when you use them, you need to convert them into dB if the specifications are listed in dB. Okay, so we'll see all of this in the example with the Butterworth filter. So the expression of the Butterworth filter is the ratio between 2 square and the whole to the n. Okay, and in the lecture, the professor said that if the omega c is normalized to 1 rad per second, these equations will be simplified to 1 over 1 plus omega square to the n, right? But we are gonna derive the equations, so let's don't normalize it for the time being. Let's just keep the omega c here, and let me explain what is omega c. So you might see omega c in your future problems. So the omega c is a -3 dB frequency. Okay, and it means that when you represent it in the dB units, when it drops from the highest point by -3 dB, the corresponding frequency will be omega c. Okay, so before this frequency, you still have a relatively high response. Good. So suppose let me see, what questions should I give you? So you'll see that the n still remains unknown, and n is the order of the filter, and it highly determines the characteristics of the filter, right? So when your n change, the sharpness of your filter also changes, and you have seen the comparison between the filters with different n in your lectures. Okay, so the situation is usually, okay, we have some specification, and then we want to know the filter, or you say the necessary parameters in the filters so we can determine it. And for the IIR and for the Butterworth filter, it's n. So the omega c is usually given, so the n basically determines its characteristics. So let's say if I want the filter to be able to have attenuation of 1 over a naught square, and what should be a satisfying n to be? So to do this, it's not that difficult as we thought. So I will show you now. The first thing is to get your filter, the expression of your filter, okay? And then you see that, okay, our omega, when omega equals to omega s, right? If we substitute it back, it should look like this. And this equation describes its frequency response, the square response when the omega equals to omega s. Okay, so this is this value. And we want this value to be smaller or equal than our specified a naught square. Okay, so this is a specification. Any question about this inequalities? Cool. So let's continue. If we move, if we reorganize the equalities a little bit to simplify it, we'll get, okay, A naught square smaller or equal to 1 plus this stuff. Okay, and then that's continuously simplify it. Okay, and then we want to extract the n. So let's take the log on both sides. Take log on the left side, got this, and take the log side on the right. You have the n out of the log, and you have a 2 here to cancel out your square. Okay, and remember we want the n, so 2 log omega s over omega c, correct? So in this way, we'll be able to get our n given the other requirements. Okay, so that's why we always want a bigger n if the left side is not integer. Okay, so only when it is bigger than this value, it is able to remain under the attenuation requirement, right? So you'll see that if we have a 5.8 here, we want n equals to 6 rather than 5. Okay, good. So let me give you an example with concrete numbers. So let's say we want to design a Butterworth filter, and we want like at least 50 dB attenuation. Notice that it is now represented in dB, okay? And then we know that the attenuation happens at 2 kHz, okay? And then we also know that the 3 dB attenuation happens at 500 Hertz. Okay, so you see that the requirements are described in text. And what should be our next step, right? So reviewing the process before, our first step should be know the specifications and they'd better be represented in our familiar parameters, right? So let's do the mapping. Cool. Okay, so anyone has any idea what the 50 dB should match to, or any other parameters like the omega p, omega s? Yes, you'll notice that the specifications are given in hertz, right? But we discuss in omega, so this also needs a conversion. Okay, so I guess you have given your answers in your heart. Okay, Aryan said 20 log 1 over a squared equals to 50. Let's see. So, we want these values, right? And we see that it is not in dB, so it should be 20 log 0 minus 20 log 1 over a squared, right? And this value should be bigger or equals to 50 dB. Sorry.
Wait, sorry, could you explain why it's 20 log 0 minus 20 log 1 over a squared?
So this is 0, and this is 20 log a squared, right? Because it is 1 over a squared. Now I turn it upside down, so it cancels out the negative side. Oh, I myself also made a mistake here. Can anyone notice? All right, so guys, you need to be careful about this. So when we say the 50 dB attenuation, we are actually talking about the h omega rather than its square. So the situation is we need to remove the square here to get our a. Okay, so log a will be 2.5, and your a will be 10 to the 2.5. Cool.
Wait, quick question. Where does the 2 kilohertz come in? Like the fact that this attenuation needs to happen at 2 kilohertz.
Awesome. So Joshua asked a question that how the hertz maps to our omega, right? Yeah, it's a good question. So Aryan said, I think that would be Fs. So what's the relationship between our hertz and our omega? So let's say the 500 hertz is FFC, because it's a 3 dB attenuation, right? So it should maps to omega c here, and the omega c is equals to 2 pi fc. Okay, and similarly, the omega s, the start band, is equals to 2 pi fs. You don't need to worry about it because later we'll take the ratio between them and the 2 pi will cancel out, which is very good. Okay, so now we get the values of A. Let's mark it with a box. And then using this relationship, we also get our omega C, omega S. Okay. Why isn't it 2 pi Fc over Fs? If the Fs here is sampling rate, I would say that it is because the hertz originally is cycles per second, right? And your omega is rad per second. So they're different only by the 2 pi factor. The sampling rate will come into place when, oh, you mean when the Fs is stop band? Yeah, we're working in the analog and S domain, so we don't need sampling rate here. Exactly. Cool. So it's a bit confusing here because the stop band is also annotated in S. So I would say omega S means omega stop band. And we're not discussing any sampling rate here, so I know you got it. Cool. So back to our formula. You see that our A is 10 to the 2.5, and our omega S over omega C is 2 pi Fs over 2 pi Fc. And it is basically Fs over Fc. And it is 2K over 500, right? And then we can get our value, okay? And the base of the log is 10 by default. And we'll get its value. So, so I believe this is something about 5. And the denominator is 1.2 something. So it's equals to 4.17. Okay. And we will take n equals to 5 to satisfy it. Cool. Any question about this?
Yeah, I guess quick question. How did you know this is the IR filter? Is it just because Butterworth is always
you
IR?
See that you can turn this textual description into a concrete Butterworth filter. And for other kinds of filter, they will have different expression of their square response. Okay. And then you just need to derive it using this method. Take log at both sides and be careful about the direction of the inequality. And or in the other way, you can directly use the formulas they give to calculate your n. And then for different filters, you have different expressions for your n requirement. And then keep in mind the direction of inequality and round it to the correct direction. And for the Butterworth filter, you always want your n to be bigger, so we will round it up, and you get the result. So you see, the IR filter design is not that difficult as you think, and I hope you can do it smoothly in your homework and probably in the final exam. Okay. So today's discussion is a little bit shorter, but I still hope that you can learn from it. And also, the left hour, the rest hour, the left half an hour in the discussion will be extended as the office hour. So feel free to ask any question. Thank you.